Okay, welcome folks. Welcome to the September Community Sync. My name is Bhavani Sudha. I am a PMC member of the Apache Hudi project. I'll be driving the community updates today. Um, we have short community updates, and then we have Raymond, engineering manager from Onehouse and Apache Hudi PMC committer, discussing through the community-driven developments like projects happening um, currently. And then we can open the floor for questions. So last month overview, this is taken from the Pulse Insight from GitHub. We had 103 authors contributing to all the PRs that landed last month. There were 244 active pull requests, 181 closed, and 144 active issues, of which 102 closed. And we've been growing in Slack. As you could see, there are we reached 2,300 Slack users and passed 3,500 GitHub stars. There are two new RFCs since the last community sync. The first one is a snapshot view management. It talks about how to better handle the snapshot view. There are two different ways that we do today for snapshot view using timeline queries and like time travel queries and snapshot restore like using save points. This RFC deals with how to improve them further to bring ideas such as lifecycle management on top of them to give better to give better support on like going back in data and like retrieving this. So take a look at this and provide your feedback. And the next RFC is on Diagnostic Reporter. This is also more kind of useful when you are reporting issues like performance issues or things like that, where we collect a lot of artifacts such as like the Spark logs, UI, what's happening in the DAG, what are the configs, etc. So this RFC delves into how can we collect this on a on-demand basis using a diagnostic reporter, so we don't have to spend time later doing this. So please go. This is also an interesting RFC. Please go through this and provide feedback if you're interested in this. So without delay, I'm handing over to Raymond to walk us through the next topic.
All right. Cool. So today I'm gonna dive deep into two major RFCs about the table, namely MetaServer and Table Management Service. These two are proposed and driven by Downs, the active contributors for the community. So MetaServer and the Table Management Service TMS so is mainly aimed to solve a problem when you have a large number of tables in your data lake. You in production, if you have like hundreds of thousands of tables, you want to manage them properly. This includes managing tables, metadata, and orchestrating those table services efficiently. MetaServer and Table Management Service is designed to centralize these management needs to reduce maintenance overhead. MetaServer also has advantages on ensuring the atomicity of sync operation between data lake tables on storage and the tables in the MetaStore. On the TMS, this also it also has a capability to allow user to decouple compute resource from the data ingestion pipeline, as in async running table services such as compaction, clustering, and so on. Those jobs can be then optimized separately based on the workload pattern. In the remaining of my part, I would dive deep into the internal design of these two components. So first is about MetaServer. This is an architectural overview of MetaServer. In the center box, we can see MetaServer has three major components within it. request handler, event bus, and storage. Request handler is responsible for receiving requests from Hudi MetaServer client, which is hooked up with Hudi commit lifecycle. Upon each write commit, client will send a bunch of different metadata about that commit, and request handler is to save them into the storage. The request will also trigger an event to allow downstream processing, such as updating other data catalog, trigger table management service, or which I will cover in later part. So what data do we store in MetaServer? There can be table-related metadata, such as where the table is the table path, the schema, table properties, what format it is, such and table type, like included there are like copy on write and merge on read table types. Also, we have partition-related metadata. We have timeline-related metadata, which is Hudi specific. Snapshot also is about at which point of time this this table is has what kind of files, and what when is the snapshot created. So let's go through this like common scenario when a MetaServer is interacting with the read and write. So first is about writing. It will first start with Hudi write client committing a write operation. Hudi meta client will send a request to MetaServer to sync this commit. The timeline service within the MetaServer will first update the commit state and record the metadata associated with this commit. Relevant commit metadata will be passed on to a partition service and snapshot service to also update partition and snapshot information respectively. Yeah, so we would usually expect adding or dropping partitions during writes, and snapshot will also be updated accordingly based on what files has been changed within this write operation. About read, how does MetaServer handle read operation from a compute engine? Usually, typically a compute engine will parse and analyzing read SQL, a SQL query to extract some analytics data. On the compute engine side, there's usually an analyzer to retrieve the analyzer should retrieve table information from Hudi catalog and to construct a relation for reading data. And it will produce some kind of analyze plan, and then in the next step is the optimizer will apply a bunch of optimization rules, such as partition pruning or predicate pushdown to create optimized plan. So in order to achieve these rules, MetaServer will need to process the predicate and return something like the filtered partition, and then pass it back so that the relation that the compute engine is trying to construct will be able to understand which files should be read, and then with the partition or information, then the relation will need to know like what files to read. The MetaServer will then ask the timeline server to ask the timeline service to get the latest snapshot from it and to get the latest the time commit and get the files from the snapshot service, which contains what files is corresponding to the latest commit or the latest snapshot, and it will return a list of file status and pass back to the compute engine. So then computer engine will be able to proceed to read those files accordingly. That's the typical read process. Another component in MetaServer is the event bus. So the core concept here is we can encapsulate all the metadata change event, like create, update, delete, into events, and then we can let the listener to receive them and push to like downstream processing components, such as another to update another separate catalog. Usually when MetaServer client will send a DDL to add a column, for example, a table service will wrap it into a change schema event. And then this is an example, like external catalog listener will receive the event and then issue a alter table request to a separate catalog. This feature is quite handy because we live in a multi-catalog world, and there will be many scenarios we'll need to sync for different catalogs. MetaServer can also support concurrency management. The core idea is we make use of optimistic locking, and it needs the storage layer to support a check and set operation. And also by introducing versioning into the snapshot, we can achieve concurrency management, and we can support also different kind of conflict detection strategies. I will walk through a typical write flow with the concurrency management support that we can achieve with MetaServer. So first of all, MetaServer client will create a requested instance on the timeline. Then it will retrieve the latest version of the snapshot from the MetaServer. So remember, the MetaServer is we need to add some version info for a different snapshot, and the version should be monotonically increasing. So with this version info and at hand, then the client will be able to associate the version, let's say we read, with the work profile that it needs to be built. It needs to build for this write. Then the next step is the instant of this write commit will be changed to in flight, meaning the writing starts, and after data is written, the transaction will start to commit the write. So that's where this this concurrency management will come into the picture. The client will first try to increment will try to set the very latest, which is the information stored on the MetaServer. We'll try to increment to set it to like we read +1. It should be a check and set operation. If this fails, means there's other write happened. So that means we need to go through the number step number 7, which is we need to retrieve all the commits committed instance after we read, and to pass it to conflict detection. So based on the conflict detection strategy user configured, it should determine if there's a conflict or not between this current commit and previous happened commit. If there's a detection, if there's a conflict, then the commit should be aborted. If there's no, then we will update the reread, which is associated with the current commit, to the very latest, again from the latest timeline from the MetaServer. then the same flow will be tried again. So it goes through a retry, goes back to step number 7 to retry. So this is a typical conflict detection workflow. We could also reduce the cost of aborting a commit by doing early detection, early conflict detection after step 3, which is building the profile. The idea is we are actually able to retrieve all the in-flight instance work profiles at that stage, because MetaServer has all the information to know what instances are in flight, and then we can detect conflicts to avoid actually writing out the data. So that will save a lot of I/O costs. Yeah, so we actually have a separate RFC, not exactly related to the MetaServer, but it's the same, based on the similar concept of early detection for the conflicts. So in MetaServer concurrency management, we can support different strategies. It can be based on commit timestamp, meaning the timestamp, the commit time instance cannot be earlier than the existing instance. It can be also based on like different granularities, like table, partition, file group, and file. So at table level, for example, the two instances cannot be committed at the same time to the same table. That's then if you go down to the file level, it's the similar strategy, but at the finest granularity, which is file. That's
so the single writer mode is the first one here or the second one?
Sorry, what do you mean by the first one or second one?
Like single writer, is it the first one listed here, or is it the second one listed here?
I mean, are you talking about timestamp based strategy?
So yeah. We have a single writer mode, right? Where we allow one writer to go through at any point in time. So is that mapping to the first bullet here, or that maps to the second bullet here? I'm not sure what is the difference between the first one and the second one.
Oh, no, these are all for multi-writer like detection strategy. I mean, they're not for single writer. This is like the first is about comparing the timestamp, like the later commit. Like if you have 2 writers, there's a later commit. It shouldn't be like earlier than the other like commit that is happened before that.
But the second one is like a single writer, right? Essentially, what you are saying is no 2 write commits can go to the same table concurrently. That's what we are essentially saying.
Yeah, I mean, if you have an in-flight instance, that also prevents that if you have multiple in-flight instance, then you should also the later happened in-flight should also be aborted, right?
Yeah. Okay, that's fine. It's not a very important question. We can take it offline too. Yeah, sure. You can go ahead.
Okay, so there are other MetaServer features that can be supported with log provider. For example, like log provider, you can use MetaServer as a log provider. As long as the storage supports check and set, then we can actually implement the log provider for multi-writer. Schema evolution, schema changes all the time, then it can be compatible or breaking. So MetaServer can actually bind the schema versions to commit instance and detect compatibility issues during writes. So that's about MetaServer. We
I
can
have
move
some
on.
questions. Should we wait for the end for the questions? I have 2 questions.
Yeah, sure. We can go ahead.
Okay. So first question is not directly related. I'm not sure if it's directly related to MetaServer, but as of now, if we see the meta sync, so even if your regular write succeeds and if your sync fails, we don't abort the regular write because the commit is actually done.
Yeah.
Your sync could fail. I saw a line item in one of your deck that atomic sync and storage or something like MetaServer and storage, atomic updates to storage and MetaServer. So are we changing that semantics, saying that if data is committed, the sync is also done, but if sync fails, we abort the data is not committed? Or am I reading it wrongly?
Yeah, that's a detailed design decision we can take. I think the RFC has not been up to date with that. But I think the idea is also to like where if the sync as in is like syncing to MetaServer itself. So, it should be atomic. But if you were talking about event bus that passing to another catalog, that's the then that should be configured like separately. That should be more like our current sync meta sync mechanism.
Okay.
MetaServer is like proxy to that. Yeah.
Okay, got it. So that means that even today, do we have a gap wherein if your sync fails, and then if you don't have any new writes until the next write kicks in, that sync is not going to kick in, right? Like we know we don't have any.
So okay, when you talk about sync, are you referring to sync to MetaServer or sync to another MetaStore?
MetaStore.
Another MetaStore, right? Yeah, I think that's the same thing about like decision we should make, whether you should fail or not. Depends on the criticalness of the sync.
Okay, got it. And then next question is somewhat aligned toward Po asked, second question. So is this MetaServer, what is the backing storage for it? Is it like
yeah, the current design proposal suggests like RDBMS, but I mean it's not like strongly bind to like RDBMS. It's like as long as it supports the check and set operation, like key value storage should also work. Okay. So people have freedom to change it. Yeah.
Okay, we have abstraction in place to plug anything.
Yeah.
Okay, got it. Okay, cool.
Okay. So yeah, about table management service. The TMS is mostly to make asynchronous jobs fully managed for data lake tables. At its core, we have like plan generator responsible for generating plans. So the generating plan is about running what services for which tables. It is a downstream listener to MetaServer event bus. We also have job scheduler and job manager. They are responsible for when and how to run the table services. They interact with orchestrators like Yan or Kubernetes. So plan generator listens for new commit completion events and decides whether to schedule a plan for running a table service or not. The decision is made based on table services strategy, which is configured at table creation. Take compaction as an example. Hudi provides different strategies to run compaction. It can be triggered like after n delta commits, or it can be based on like the cumulated log file sizes. The strategy can be modified by user while issuing a DDL to the table. We do not allow configure the strategy while writer in order to handle multi-writer scenario, because multi-writer can have conflicting strategies. So once the strategy decides that based on strategy, we decide to run a compaction, the plan generator will make a requested compassion commit to the timeline in MetaServer. And also it will save the plan info as into its own storage. The plan will be then ready or waiting for scheduling. So move on to the next step about job management. So as mentioned, there's a pending action plan, pending compaction plan that is saved into the storage. This jobs scheduler will continuously pull the information and see what pending plans needs to be executed. And the execution for the plan can be also the scheduling for the plan can also be based on some like strategies, for example, like first in, first out, or priority based. The execution will then be dispatched to a job manager. So the job manager is responsible for submitting the job to a separate orchestrator. And also a job manager will keep polling and also saving the job states. Job manager will support submitting jobs for different engines and also support auto retries, monitoring, and alerts so as to manage these jobs. Okay, that's all about the detailed designs. I want to do also a big shout out to the contributors from ByteDance, namely Xiaoyu and Zhao Jing, who are driving MetaServer and table management service respectively. Zhao Jing is also a committer from Hudi. The ByteDance team and reviewers from Hudi community also have a very good collaborative experience. We have weekly sync meetings, discuss the implementation and plans, review and comment on the design over GitHub. It's a great experience, a collaboration experience. So that's all about.
Yeah, I have questions about the table management service. So I'm thinking about like a very simple user. Okay, they have a single writer. Okay. But multiple tables. So they want to use this table management service.
Okay.
And the writer just schedule inline, okay, but let the table management service take care of just the execution. So in that case, for example, you don't even need assuming if metadata is disabled, then you don't even need a log provider, right? I am assuming in this, we definitely need a log provider between the table management service and the regular writer. Is my understanding right?
Yeah, it will use a log provider. Yeah. And MetaServer actually works that way. Yeah.
Okay. So for the use case that I'm talking about, we can get away without the log provider, right? If you do scheduling internally within the writer, okay, it's pretty much like the Delta streamer with async tables. Like we have a separate thread here, we have a separate process or like the service to do the execution alone for you.
Yeah. I mean, it as I said at the beginning, it mainly aimed for handling a large number of tables.
Large number of single writer tables is what I'm talking about.
Yeah.
So in short, my question is scheduling can be done inline and just offloading, delegating the execution to the service, or is it designed in such a way that both scheduling and execution is done by the management service?
It's designed for scheduling also with both with TMS.
Okay.
Yeah.
I see.
It's supposed to kind of centralize all these related features in like one server, so that
I see. The reason why I was asking is I understand execution is costly, but scheduling is not costly, right? For a given table, if there are no multiple writers, why do we need to actually make a remote RPC call and then wait for it to actually do the scheduling? And then
I mean,
your write is blocked during that. Your regular write is blocked during that scheduling phase?
You could scheduling. I mean, you could do like more smart scheduling if you have a centralized service, right? You can decide whether you want to run some writer first or deprioritize another.
Okay. I mean, again, you're talking about multiple writers to the same table, or you're talking about multiple tables trying to schedule? I mean, different tables. I'm talking about a single writer to a given table, not multiple.
Single writer to a given table. I mean, if there's just one table, what?
No. So, there are 1,000 tables, but for a given table, there's only single writer. There is no multiple.
Yeah. I mean, even if you have a single writer to all the tables, like they can also be scheduled accordingly, right?
Yeah. I'm not saying that the TMS can't be scheduled. Will the TMS see the scheduling is when let's say the TMS is trying to schedule something, a trigger like a schedule for compaction for a given table. There you're not going to incorporate any intelligence about what are the other tables in flight or something, right? You will look into a given table and try to understand like the compaction strategy, whether you take based on log files or number of commits or that sort. The TMS is not going to bring in other tables in play here while trying to.
Why do you think it's not? Because all the plans that is saved into the RDBMS, right, in the storage of TMS, and the scheduler should be is aware of all the tables, what they are gonna do about table service.
Oh, probably my words were confusing. I am talking about the plan generator. Probably my words were overloaded.
Okay.
So what I'm saying is, okay, so for now we have something called compaction plan generator and then compaction executor. Okay, I'm talking about the first phase.
Right.
The plan generator in TMS, if you get a trigger to plan something for a given table, it doesn't have any bearing on any other tables in the cluster, right? Or are we adding any intelligence there, even to schedule or generate?
No, it's mostly, it should be mostly based on the strategy.
Okay. So that's what I was coming to. So that means if there is only one writer for a given table, that is.
I get your idea. You're basically saying this can be still like offload to like.
You can keep it locally. You can keep it locally if at all there is a single writer per table.
I mean, it's really a design choice whether you want to do it centralized within the server because all these things happen together, or you want to let individual writer to decide on the plan. I mean, there's not much like big difference, but I feel like if you have a design.
Why I was kind of talking about this is I synced up with Uber people recently. They haven't, so for some of the tables, they haven't enabled metadata table, if I'm not wrong. So for them, from an operational standpoint, keeping the plan generator locally for each writer, because they don't have multi-writer for a given table. They have only single writer. At least from what I heard, they are just delegating the execution because that keeps things simpler. That's what they told me. I haven't got into much detail whether they tried the first approach, they ran into issues, and then they went with the second one.
I can think of one like maybe a use case about like if you have centralized this plan generation in the server, you could actually easily build some like a dashboard to see, okay, what's the plan is generated for which table. But yeah, I can see that. I mean, there could be, it's again, I think it's just a design choice. I'm not sure about like what's exactly the problem.
Another thing to think about is how long the time of locking. If it's going to be a remote call, definitely it's going to be a little more expensive compared to doing a local locking, right? Maybe that could.
Locking. Yeah, I mean, Yeah, it could be. I mean, the log, yeah, MetaServer is supposed to work closely. There's actually some idea about like log provider. Why can't we have them together, like MetaServer and table management service? But yeah, it's I think there should be a different like component based on different use case.
Okay, got it. So both MetaServer and this table management service are all optional, right? These are add-on things that users can enable or disable.
Yeah. I mean,
okay.
it's a totally separate component.
Okay, got it. Okay. We don't have questions from anyone else.
Hey, Raymond, can you let Kyle in? I think he's waiting to get in.
There are actually people. Oh, okay. Okay. I'm not sure when did Kyle requested to join, but
just a few minutes. We're fine.
Okay. Oh, okay. Yeah, if there's no more question, we can end this early. Paul has a question. What is MetaServer running on? A database? I mean, MetaServer is like just a normal like a server, like backend server, but it should also has a like storage layer, like a database. Yeah.
Okay, that makes sense. Can we use DynamoDB for this?
Yeah.
build?
Yeah.
Okay.
It should support key value like store as well. Yeah. Yeah, one of the requirements to support like the check and set operation, so that to support the concurrency management.
So with respect to okay, since there is no other question, so I haven't read the RFC or implementation, so it's all raw questions. So for the scheduling, can we assign weights? I know you, and the first simpler strategy is FIFO.
Sure.
So for example, you could give more weights for, let's say, compaction compared to a clustering, something like that. Is that strategy there? What are the different strategies we have currently?
I mean, this kind of detail wasn't illustrated in the design doc, but I can think of like definitely you can add ways to, for example, like the plan. When people when it's the plan generator generates a plan, right? It knows what table it is. I mean, you could kind of assign some weight for that table. Is that what you're thinking about weight?
Oh, you're okay. You are talking about across tables. I was talking about within a single table. If you have both clustering and compaction, scheduled, okay, which one will the job manager or the job scheduler will prioritize?
Then I think then it's about like we could have this is more like extended feature for like strategy when like, based on current strategy. If we add maybe a new like field for strategies to have weights, then yeah, we can achieve weights as well.
Okay, got it. Okay. So the plan generator also will pretty much accommodate. So for example, if we already have a in-flight compaction, whether can we trigger more compaction plans for a given table? That is pretty much works as of today. So that there's no major change there.
Yeah.
Okay. Okay, that's it from me.
Okay, cool. I guess that's all for this sync call. Okay.
Great.
Thank you, everyone.
Okay, thanks.
Thanks, Raymond.
Thanks, you.
Yeah,
Take care.
thanks, Raymond.
Thank you, Raymond. So,
Thanks, Raymond.